Hello everybody, welcome back to another tutorial. This time we will do an inclined frame analysis. We'll analyze the frame shown in the figure, try to get the normal force diagram, the shear force diagram, and the bending moment diagram. So the question say, draw the normal force N, the shear force V, and the bending moment M diagrams for the frame shown in the figure. Okay, so we have this frame with the distributed load, triangular distributed load as shown at member CD, and we have one concentrated load acting at the middle of member AC, and we have the dimensions of the total frame as shown. So let's get into it. The solution: step number 1, concentrate all distributed loads. Because we want to calculate the reactions, we need all the distributed loads to be concentrated. We only have one triangular distributed load at member CD, so we'll start with that. Triangular load, when you concentrate the distributed load, you basically concentrate at a distance L/3 from the high end, and of course 2/3L from the zero end, which is the left side in this case. And the value of the load is basically the area of the triangle. 1/2 times 4, which is the length of the member, times 3, which is 3 kilonewtons per meter. And that's going to give me 6 kilonewtons per meter. Okay, that's step number 1. Step number 2, we will try to apply the equilibrium equations to obtain the support of the reactions. So what are the equilibrium equations I'm talking about? We'll try to apply the summation of the forces in the x direction to be equal to 0, the summation of the forces in the y direction and set that equals to 0, and we will pick a point and take the summation of the moments above this point. First, we need to define the reactions. So at A, we have AY pointing upwards, we have DY at D pointing upwards, and we have DX pointing to the left. The reason I chose DX to be pointing to the left is I'm expecting it to be this way because I have 10 kilonewtons pointing to the right, so this support should resist the 10 kilonewtons. Anyways, if you assumed it in the other direction, that is to the right, and if you do the equilibrium equation, you will see that the result of dx is going to be negative. So that means you have to switch the direction of your assumption. So let's go on with this assumption. We will do the summation of the forces in the x direction and set that equal to 0. So I have dx minus 10 equals to 0, or you can say it the other way: 10 minus dx is basically 0. Okay, and if I solve for dx, I'll get dx equals to 10 kilonewtons. It might be a little bit confusing the way I wrote it. It should say minus dx plus 10 equals to 0. And if you solve for dx, it's going to be again 10. But anyways, the way I assumed it, 10 is opposite of dx. So if 10 is positive, dx is negative. If 10 is negative, dx is positive. If I do the summation of the forces in the y direction and set that equals to 0, I will have ay minus 6 plus dy equals to 0. And I will get an equation saying ay plus dy equals 6 kilonewtons. Now jumping into the third equilibrium equation, if I do the summation of the moments about point D, and the reason I picked point D because I have dx and dy basically going through the point of interest, so the dx and dy will play no role in the moment equation. So if I do this, I'll have ay multiplied by 7, which is the total distance between the total perpendicular distance between A and the projection of D, and that's going to be negative because it's going to be clockwise, and it's opposite to the positive sign convention I chose. Then I'll add 10 multiplied by 2, and that's a positive because it's going along with the sign convention, plus 6 times 4 over 3, and that should equal to 0. And if I solve for AY, I'll get 4 kilonewtons. Now I can go back to AY plus DY equals 6, and I solve for DY. 6 minus AY, 6 minus 4 equals 2 kilonewtons. So in summary, I have AX, AY, and DY as shown. Now, step number 3, we will work on each member separately. So we will disassemble the frame, we will work on AC by itself, and then work on CD. First we need to resolve inclined forces into two components, parallel and perpendicular to the member local axis. And if it's not clear yet, the next slide should clarify this thing. Then we will reorient the members and the forces to the global XY system. So in this case, I have an X and a regular Cartesian system, X and Y. If I'm having any inclined members, I have to rotate them to match the of course you need to rotate the inclined member to match the X axis. It makes more sense. Then we will solve for the forces and the moments at the common joints with the next member. So in this case, joint C will have common forces, common shear forces, and common moments, but the word common does not mean that they are equal. The reason is because I'm disassembling these members from this joint C. So I need to know what are the internal forces at joint C that is acting on the segment AC and the segment DC. Okay, so let's go ahead, and hopefully it's going to be clearer in the next slide. So member AC, this is the member, and guys, I need you to focus here because this is the tricky part of the whole problem. Okay, so if I have this member AC, okay, and before I continue, I need to find the length of the segment AC. So segment AC is basically the hypotenuse of the right triangle, okay, which is the length of AC will equals h, the hypotenuse, equals the square root of the adjacent squared plus the opposite squared. So AC basically equals the square root of 3 squared plus 4 squared equals the square root of 25, and that's going to give me 5 meters. So that's the length of member AC is 5 meters. Alright, now the cosine of theta, and now I'm going to show you the theta. The theta is basically, let me just skip ahead to show you the theta. This is the theta. The cosine of this angle is basically the adjacent over the hypotenuse, the length of the adjacent, which is 3 over 5, the hypotenuse. And the sine of this angle theta is the opposite over the hypotenuse, which is 4 over 5. So whenever we see a cosine theta, we substitute it by 3 over 5, and whenever we see sine theta from now on, we substitute it with 4 over 5. So cosine is going to be 3 over 5, sine will be 4 over 5. Okay, what about these red arrows? These red arrows are the basically the components of each force. The 10 kilonewtons, I said in the previous slide that I'm going to resolve it into two components, one perpendicular to the member and one parallel to the member. The same thing goes for the AY reaction, one perpendicular and one parallel. Okay, now I'm going to use this theta and try to get the theta that's going to help me resolve the force 10 kilonewtons or the AY. So if this is theta, as shown, this is going to be theta. You can see the thin line of theta at point A is parallel to basically the 10 kilonewtons, so this theta should equal that theta. And using the same logic, this is going to be theta, because the red arrow that's parallel to the member AC, I just said it, it's parallel to the member AC, so these thetas should be equals. So now I know the angle between the force and one of the resultants. Okay, so this way I can say, for example, for the perpendicular component is going to be 10 times sine of the angle. 10 is the magnitude times sine of the angle. So 10 multiplied by 4 over 5. Remember, whenever we see a sine theta, we substitute it with 4 over 5. That's going to give me 8 kilonewtons. Do the same thing for the parallel component. 10 times the cosine, which is 10 times 3 over 5, equals 6 kilonewtons. Okay, now we need to focus on the resolution of the AY. How can we do this? If I create this perpendicular or this right angle, 90 degrees, if this is theta, the rest is basically 90 degrees minus theta. And this is going to be theta if I create a new right triangle. So theta plus 90 over theta, theta plus 90 minus theta will give me 90. So in this way I'm moving the original theta to this new position. Theta, then 90 minus theta, then theta. Okay, now if this is theta, this is theta. Why is that? Because the perpendicular component of AY is parallel to this black line. Alright, now I know the angle between this force and one of the components. Basically I'm going to say AY times sine theta is for parallel component equals 4 times 4 over 5. That's going to give me 16 over 5. And for this one is going to be AY times cosine theta, which is 4 times 3 over 5. That's going to give me 12 over 5 kilonewtons. Okay, enough with this mess. Let's clean it up. So this is what I have. Now this is the beam I'm going to be working with. Okay, now if I take a section at C, cut a section, try to expose the internal forces, I have a normal force, I'm having a shear force going downwards, and I have a moment that's going counterclockwise. Now my goal is to solve for these forces. Okay, again, equilibrium equations. Summation of the forces of the x will give me 16 over 5 plus 6 plus NC equals to 0. NC will equal minus 9.2. Summation of the forces in the y direction, I'll set it equal to 0. So 12 over 5 minus 8 minus VC equals to 0. Then VC is minus 5.6. Now I'll take the moments about point C, set that equals to 0. So MC, then I'm going to start from the left end of the beam. I have 12 over 5 multiplied by 5, and it's a negative sign because it's going clockwise. And remember, the counterclockwise is the positive sign convention for the moment. Then I go to the second force, which is the 8. You can see that I skip the 16 over 5 and the 6 kilonewtons because the line of action for both of these forces go through the point of rotation, which is point C. So they don't play any role in the moment equation. So for the 8 kilonewtons, multiply by 2.5, and it's a positive, and the whole thing said I should set it equals to 0. I'll get MC equals negative 8 kilonewtons meters. You can tell if you can see that all of my values here are negative. So if I want to draw the final beam with the internal forces exposed, I should switch all the directions. So that concludes the part for trying to find the internal forces for the inclined member, or the first member, which is member AC. Now let's move on to the second member, member CD. This is member CD. We have this triangular distributed load. If I concentrate the load, again 6 kilonewtons as before, and it's acting at 2/3 from the left or 1/3 from the right, and if I substitute L times 2/3 or 1/3, I get the values as shown. These are the reactions, and on the left I have these internal forces exposed. Now the sign convention, if you are cutting the member and looking at the right segment, is going to be as shown. If you are looking at the left segment, everything should be switched. Okay, summation of the force in the X, I'll have minus 10 minus NC equals to 0. So NC is minus 10. Summation of the forces in the Y, 2 minus 6 plus VC equals to 0. So VC is 4. And summation of the moments about C equals to 0. MC plus 6 times 8/3 minus 2 times 4, that 2 times 4, the total length, that's equals to 0. And if I solve for MC, I'll get negative 8 kilonewtons meters. Okay, so this is my final beam after making sure that I've changed the direction for the moment, because I assumed it to be clockwise, but I got a negative value, so I changed it to counterclockwise. And for the normal force, I assumed it to be to the left, and it turns out to be negative, so I'm switching it to the right. But for the shear force, it was positive, so I didn't change it. Now step 4, draw the normal force N, shear force V, and the bending moment diagram for each member. So let's start with this member, member AC. Just trying to set up the problem here. Okay, so let's start. For the normal force, I'm gonna go down minus 3.2. A question will be, why do you go down? And why is it 3.2? Okay, let me answer this backwards. 3.2 is basically the 16/5. And I'm going down because I'm assuming that if the member is in compression, I'm going to assume it to be negative, and if the member is in tension, I'm going to assume the graph to be a positive. Okay, how do I know it's the member in compression? If I take a small cut between A and B, alright, I'll have an arrow pointing to the left, to the right from point A, and at the cut, to make the segment in equilibrium, I should have an arrow pointing to the left. So the small segment is in compression, so the whole thing is in compression. Globally, if you look at it, 9.2 kilonewtons is pushing to the left, and 16/5 and the 6 are pushing to the right, so the whole thing is in compression. So between point A and point B, straight line, because I'm not having any forces that's changing my values for the normal force. At point B, I'll have a jump of -6, because again, if I take a cut between B and C, now if I take a cut between B and C, and I need to add a left pointing arrow at the cut to find an equilibrium between the 3.2 and the 6 that's axing to the right, then I need a 9.2 to the left. So the segment between A and the point of cutting between B and C is in compression. So again, the whole thing is in compression. So at point B I have -6. I go all the way to the right, then I'm gonna have a compression at point C, -9, which is gonna go upward. Okay, now I believe that's a mistake. That should be a 9.2. Okay, let's move on to the shear force. For the shear force, I'm gonna go up of a value 2.4. The 2.4 is basically the 12/5, and it's up because the force 12/5 of the 2.4 is trying to push me upward. Between A and B there are no forces acting up and down, so I go a straight line. Then I'm going to be pushed down 8 units by the force 8 kilonewtons. So from positive 2.4 to negative 5.6. Again, between B and C, no forces, so I go to the right. Then I'm going to be pushed up 5.6, and my shear force diagram will be closed. Alright, now for the moment, the at the left, which is A, there is a roller, so it starts with a 0. And at B, basically the value of the moment at point B is the area of the shear force diagram between the roller, or point A, all the way to B. Alright, so it's 2.4 multiplied by the segment AB, which is 2.5, because the whole length of the member is 5, and I'm gonna get 6. Now I know that the moment diagram should go down, alright, because remember, this is the maximum positive, because at this point the shear force crosses the x-axis. The shear force diagram crosses the x-axis. But to what value at the negative I should go? If I look up, I have a negative moment acting at point C of a value of 8 kilonewtons, which is 8 kilonewtons meters, which is a negative value. So the graph should go all the way to this value, -8, and closes. Alright, now let's move on to the next one. The next one is a little bit trickier. So this is the next basically member. If I try to do the normal force, it's obvious the whole member is in compression, and the compressional force is -10. So I go -10 all the way and go up again. For the shear force, it's a little bit not clear, so I'm going to draw it over here. I know that it starts with a 4 going upward, and it ends with a 2 at the negative side. That's basically the values I'm getting from the graph. And it's going to be concave down, or going down like this, because the shear, the load diagram is a linear function. So it's from the first degree. And the shear force basically is a result of integrating the load equation. If the load equation is from the first degree, that's x, for example, I'm going to have the shear force to be of second degree, that's x squared. So it's not a straight line. Okay, but the problem here is trying to find where the shear force diagram crosses the x-axis. So let's look at these values, 4 and -2. We agreed on that. I know it crosses at distance x, and the rest is basically 4 minus x. Alright, I'll try my best now to solve for this value x. This is the load diagram. Alright, and my first thing to do is try to calculate this area. This area represents the excuse me, this area. If I calculate this area, which has a which is an area of a triangle with a base x and a height y, so the area is basically 1/2 xy, and that should equal to 4. Why 4? It's basically the value of the shear. Alright? Now, this area, if I try to calculate, it's 1/2, it's a trapezoid. So 1/2 y plus 3, y plus 3. You can look up the rule for calculating the area of a trapezoid from any website you want. But basically it's the average of the two sides multiplied by the distance between these two sides. So taking the average is y plus 3 over 2. And the distance between these two sides is 4 minus x. And this area should equal to 2, which is the value of the shear at the right. Okay, if I set these areas, I'm not setting these areas equals, but if I try to solve these two equations simultaneously, I can get a value of x and y. And if I do so, I'll get x equals 3.26 meters, and I'm gonna get y to be 2.45 kilonewtons. Okay, now I know the value of x, the value of y. I can go ahead and draw the shear force diagram. Alright, now with the moment. The moment diagram, we need, because it's a little bit complicated, it's easier. Let's go back here. The way we used to find the moment values is by calculating the area under the shear force diagram. But since the shear force diagram here is not a regular shape, it's not a triangle, it's not a square, so it's hard for us to find the area under this curve, unless if you know the equation you can integrate. Alright, but you don't have the equation yet. You can come up with the equation if you want, but I'm assuming you're doing this in an exam where you're trying to save time. Okay, so the way to do it is by cutting the beam at the point of interest. Where do you want to find the shear force? I mean the bending moment value. Going back again, we're trying to find that we're trying to find the maximum moment. The maximum moment takes place at where the shear force diagram crosses the x-axis. Okay, so it's at x equals 3.2 meters. So I cut the beam at x equals 3.26 meters. I concentrated the load from the triangle distributed load. I introduced the left internal forces. Now, and as for the value of this triangle, it's 2.45 kilonewtons per meter now, because this is the y value we solved in the previous slide. Okay, I defined all the lengths, 2 over 3 times 3.26 and 1/3 of 3.26. Now I'm ready to apply the equilibrium equations again and solve for Vx and Mx. But remember, I'm trying to find Mx. Vx here definitely will equal to 0, because that's where the maximum moment takes place. So I'm interested in Mx. So solving for Mx, I get Mx plus 8, which is the concentrated moment at the left end, or the internal moment, I mean, minus 4 times 3.26 plus 4 times 1/3 of 3.26, set that equal to 0, and if I solve for Mx, it's 0.7 kilonewtons meter. So this is my moment diagram. Alright, I go down by 8 because I have a concentrated moment at the left, and I know there is a positive value reaches 0.7 in the that's a maximum value of 0.7 somewhere before the end of the not actually somewhere, it's at 3.26 meters from the left, and I must go down all the way to 0, because remember, at the point D, which is the right end of this segment, I have a hinge, so the moment should be equal to 0. So that's why I'm having this shape. Now the final steps here is try to combine all the diagrams for the two members and on the entire frame. So this is the value of the normal force diagram. This one is for the shear force diagram, and this should give me the bending moment diagram. Alright, and that's it. Hope to see you soon in another tutorial. Thank you.